In the world of building wire, there are several common choices available that at first appear quite similar. Some of the most common of them are THHN, THWN, and Romex. THHN wire is thermoplastic high heat resistant nylon coated wire, that is a single conductor wire with PVC insulation, and a nylon jacket. It's commonly used in conduit as electrical wiring for buildings. Its heat and oil resistance, which makes it suitable for appliances and machine tools. THWN is essentially the same as THHN and the two are often used interchangeably. THWN is also a single conductor wire with PVC insulation, and a nylon jacket. The key difference is the W in the name, which indicates water resistance. THWN is rated for temperatures up to 90 degrees Celsius in wet conditions, versus 75 degrees Celsius for THHN. Romex wire refers to the trade name for thermoplastic sheathed cable, TPS. Romex is often used as residential wiring for electrical circuits and lighting. We generally think of a specific type of Romex, which is known for its non-metallic sheathing, and primary use as branch wiring. This is referred to as Romex NMD, or B. Recently, Nexans Canada introduced color coding to its line of non-metallic sheathed cables, to enable easy identification of the various sizes commonly used in residential construction. These copper conductor cables are used mainly to distribute power to outlets, lights, electric ranges, dryers, and other equipment. This type of cable is commonly known by trade names, such as Romex or Canadex, but the Canadian Standards Association CSA type is NMD 90, meaning non-metallic, dry location, 90 degrees Celsius rated. Nexans now supplies NMD cable with color jackets. Cable for use with 15 ampere FC is supplied with a blue jacket, and the cable for use with a 20 ampere kitchen GFCI has a yellow jacket. As well, 2 conductor number 14 AWG copper NMD, used for other 15 ampere circuits, is supplied with a white jacket. All number 12 AWG copper for 20 ampere circuits, has a yellow jacket. All number 10 AWG copper for 30 ampere circuits, has an orange jacket, and cables for over 30 amperes have a white jacket. The jacket color coding is not required by any electrical code, or by CSA product requirements. However, Nexans supplies the color-coded products as an aid for installers and inspectors in identifying cables used to supply the 2 special types of circuits mentioned above, and to indicate copper conductor size. In doing so, Nexans makes the job of cable identification quick and accurate for the contractor and inspector. Voltage drop is the reduction in voltage in an electrical circuit between the source and the load. Wires carrying electricity have inherent resistance, or impedance, to current flow. Voltage drop is the amount of voltage loss that occurs along a circuit due to this impedance. For equipment to operate properly, it must be supplied with the right amount of power, which is measured in watts, which is calculated by the product of current, amps, times voltage, volts. Motors, generators, tools, and anything that runs on electricity, is rated for power. The correct amount of power enables equipment to meet its design power rating, and operate efficiently. Too much, or insufficient amounts of power, can result in inefficient operation, wasteful power usage, and even equipment damage. That is why understanding voltage drop calculations, and selecting the correct cable for each application is so important. The National Electrical Code, NEC, catalogs the requirements for safe electrical installations, and represents the primary document for guidance, providing direction for both trained professionals and end users. These codes set the foundation for the design and inspection of electrical installations. For branch circuits, the NEC advises that conductors, for feeders to dwelling units, should be sized to prevent voltage drop exceeding 3%, and maximum total voltage drop on both feeders and branch circuits should not exceed 5%, for reasonable efficiency of operation. In addition, when dealing with sensitive electronic equipment, it states that voltage drop on any branch circuit shall not exceed 1.5%, and the combined voltage drop on branch circuit and feeder conductors shall not exceed 2.5%. It is important to note that much of the equipment manufactured today contains electronics that are particularly sensitive to excessive voltage drop. Ampacity A cable's electric current carrying capacity is also connected to voltage drop. The code stresses the importance of accounting for voltage drop when considering a cable's ampacity rating and the need to satisfy both requirements. In order to understand voltage drop, let's consider the simple circuit in this diagram. A voltage source of 110 volts AC is connected to a load resistor of 11 ohms. According to Ohm's law, the current that will be drawn by the load will be equal to the voltage divided by the resistance, which in this case will be 10 amps. Looking at the same components, but this time, with two 11 ohm resistors in series, we still have a voltage supply of 110 volts, and Ohm's law tells us that current will be 5 amps, and the voltage drop across each resistor will be 5 amps times 11 ohms for 55 volts. Let's add 8 more resistors, and reconfigure the circuit to look like this. The current in a circuit will now be a function of the supply voltage, divided by the total resistance, which is made up of 10, 11 ohm resistors. Using Ohm's law to obtain a current in a circuit, we use the supply voltage, divided by the total resistance, and substituting actual values, we get 110 volts, divided by 110 ohms, or 1 amp. We can easily calculate the voltage drop across each resistor now by multiplying the current times the individual resistance of 11 ohms, which works out to 11 volts. Now let's add a load of 10 ohms to the circuit. The total load now becomes the 10 resistors, plus the 10 ohms of the load. The current of the circuit is now given by 110 volts, divided by 110 ohms, plus the load of 10 ohms, which equals 0.92 amps. This time we are interested in the voltage drop across the 10 ohms load, which is given by the current times the 10 ohms load, which equals 9.2 volts. Let's add some realism to the situation, and suppose that the load is a 100-watt incandescent light bulb. The equivalent load resistance of a 100-watt light bulb, which is essentially just a resistor that emits light and heat, is given by this equation. Plugging in the actual values, if the light bulb is connected to a 110-volt power supply, the equivalent resistance would be 121 ohms. I am making one other change to our circuit. And that is, I'm going to change each of the individual resistors, R, to 0.25 ohms. That means the calculated circuit current will be 110 volts, divided by the total resistance of 2.5 plus 121 ohms, which equals 0.89 amps. With that amount of current flowing in the circuit, the voltage drop across our light bulb will be 0.89 times 121, which equals 107.8 volts. This is interesting now, because the light bulb was rated at 100 watts, which was calculated for a supply voltage of 110 volts. The physical makeup of the light bulb has not changed, which means our calculated resistance also has not changed. It is still 121 ohms. In our circuit, the voltage drop across the light bulb has been calculated at 107.8 volts, and the current in a circuit has been calculated at 0.89 amps. Therefore, the light bulb will be dissipating 95.9 watts. This means that the output light will be reduced in brilliance by about 4%. The total resistance in the circuit of 121 ohms is the same as connecting a power source to the light bulb with a length of number 14-2 AWG copper wire. This points out the fact that even copper wire has some resistance, which does become significant over some distance. Although a 4% drop in light bulb brilliance is not that significant. Given more light bulbs, or more length of wire, the percentage drop across each light bulb will decrease, to a point where it starts to be significant. This becomes even more significant if the load were a motor, such as a water pump, because the voltage drop across the pump is made up of both resistance and back EMF. The back EMF of a motor is related to its speed of rotation, which is related to the applied voltage, so the drop in voltage is not just 4%, as in the case of a pure resistive load. Instead of the load being purely resistive, let's replace it with a motor whose back EMF and internal resistance provides the same voltage drop as the 10 ohms load did. This means that the voltage drop will be greater than 4%. Which ultimately means more current is going to flow for the same amount of work that is being done. Over time, and depending on that time. This means the windings of the motor will begin to heat, and ultimately overheat, causing damage to the motor. Taking into consideration the characteristics of a motor. The reduction in voltage may mean that the speed of the motor does not have enough energy to get past the inrush current, exacerbating the whole situation even more. This information, as well as other related electrical blogs, may be found on my website at https://www.getpspt.com. There you also have access to my courses, which are continuously being added to, and at the present time include the following.